Are LLMs like harder to learn than other kinds of concepts?
It's a matter of understanding the building blocks that go into an LLM. They're not extremely complex. Once you dig into them and get your head around them, it'll be a game changer for your future career. Like, the new hot thing is LLMs, and all these companies, like the ones that want to be at the cutting edge of technology. We're talking about real estate companies, banks, insurance companies, consulting companies, and of course, all the tech companies. Predicting the next word is sufficient in order to behave like a human, in order to think like a human, in order to create things like a human.
Kirill, welcome to the Super Data Science Podcast. You've been here so many times, actually, even since I've been host of this show. But many of our listeners probably know you as the founder and the original host of the Super Data Science Podcast. You hosted it for 4 years. And now that we're in 2024, it's been more than 3 years that I've been hosting. So by this time next year, we'll be neck and neck in terms of total episodes hosted.
Yeah, for sure, for sure. Very excited about that. Hello, everybody. Welcome, welcome. I'm excited. Welcome me. I'm excited to be back on the show. And yeah, John, the time flies. Like 3 years that you've been hosting. It's how do you feel?
I feel a lot more comfortable than I did the very first
Yeah.
episodes. Kirill prepared for me this huge document, it's like 30 pages long, which was amazing. This was before ChatGPT, so he typed that.
For sure, yeah.
And it had just tons of useful tips for me getting started on the show. Um, and then we did one episode co-hosting together, and then
Yeah,
all of a sudden that was it. I
yeah.
was thrown in the deep end. And so those first few episodes, I was certainly a bit nervous, but now it's 2 episodes a week, so I'm pretty comfortable. Every once in a while we have a guest on that I'm intimidated by, I'll tell you that.
Yeah, yeah, I know
You're
the
not one
feeling.
of them.
Oh, good. Good, man. Good.
Yeah, it's so great to have you here. Where are you calling in from, Kirill?
Australia, Gold Coast, as usual for me these days.
Usual
And
place, yeah.
you're in Canada, right? With family.
I am in Canada with my family, so we're recording this one over the holidays, and I've had a
Yeah,
wonderful time here. Yeah, yeah,
yeah.
yeah.
3 more days left of 2023. It's been a crazy year with a lot of AI, ML breakthroughs, and LLM is the new big thing, right?
Yeah, for sure. LLMs, they have been a big thing for a while, but certainly the end of 2022 was when, with the release of ChatGPT, people, I think, became aware of at least the technology, the user interface of
Yeah,
this technology.
yeah.
And so, yeah, it's exciting to have an episode now dedicated, Kirill, to large language models, which no doubt throughout 2024 going to continue to be a huge deal,
Yeah, for
and
sure.
for years beyond. I don't
Yeah.
think there's any doubt that it's. I think the thing that replaces LLMs is probably some ways away. It'll probably be things that kind of combine. I think what's next in AI will probably involve still LLMs. So everything that you're going to cover in today's episode is going to be relevant for a long time. I'm super excited about the content that we're covering today. I can't wait to learn from you.
Thanks, man. I'm super pumped as well. Like preparing for this podcast. Um, I guess I'll start a bit earlier. Last time we appeared on the show with Lan, we were talking about cloud computing. That was
Yeah, that
about
was
8
episode
months
number
ago.
671.
Exactly. Yeah.
671. It was in April 2023.
Yeah. So about 8 or 9 months ago, and we're talking about the necessity of cloud computing for machine learning and data science moving forward, and for AI as well. And I just wanted to reiterate that that's still the case. We're still very focused on that. We're helping a lot of people since that episode. That's because that was when we were launching our platform, CloudWolf. Since then,
Mhm.
over 400 people have signed up, and most of them are data scientists, machine learning engineers. Dozens have received the AWS certification. And so we're very pumped about that. And it is still like the case more than ever that cloud is important for machine learning AI. But we're not here to talk about that. We're here to talk about LLMs. And why is that? Because um, initially, like at the start of this year when ChatGPT came out and things like that, or start of 2023, I didn't think that there'll be a lot of demand from machine learning practitioners and data scientists and AI engineers to learn the nuts and bolts of transformers, large language models, GPT models, how they reconstruct. I thought it would be focused on prompt engineering, but I was very wrong. Like we've had like a lot of demand for a large language models course, and also we're seeing a lot of employers out there starting to hire LLM engineers. It's a very hot space. It feels to me like remember in 2012, like data science was the new big thing, and data science salaries were like through the roof because there was lack of talent. Nobody knew what it meant. Nobody knew hiring managers didn't know who to hire. Like it feels that all over again. Like this had been a 10-year cycle. Now the new hot thing is LLMs, and all these companies, like the ones that want to be at the cutting edge of technology and implement LLMs inside their operations, inside their I don't know a business, whatever else, however they're doing their business. And it's not just tech companies. We're talking about real estate companies, banks, insurance companies, consulting companies, and of course, all the tech companies. And the salaries for LLM engineers are through the roof, like going up to all the way up to 600,000 for LLM manager or 500,000 for LLM engineer. What do you reckon? Do you think we're at that phase again with like data scientists we were like 10 years ago?
I definitely agree. I think it's a compliment to the data scientist skill set. And I think that because of innovations like LLMs, we have had continued interest and increased interest in data science roles, machine learning engineer roles. It's one of those things where people worry about automation taking jobs, but
Hmm.
automation throughout all of history has changed the kinds of jobs that people have. And this is a perfect example where the ecosystem around data science keeps developing and the tools that we have grow. And so, even though large language models make data analysis easier, making models easier, allow us to have all kinds of automations, the demand is greater than ever because of this ecosystem that evolves and because of the kinds of applications that people expect more and more to incorporate these kinds of technologies. And so, the only, I guess, kind of uh, bit of nuance that I would add is that I don't think it's that like 10, 12 years ago, data scientist was super popular and that's like waned.
Mm.
It's just that this particular niche within data science has now exploded as well.
Yeah, yeah, yeah. I completely agree with you, and I think there's this like once something new like this happens, or if we learn. I love what's his name, that investor in the U.S. I forgot his name. The one who looks at like past to predict what's going to be future. It's natural, right? Like if we look at what happened with
I only trust investors that look into the future. Just
I know, like he has a book, Ray Dalio. He has a book recently about like economies and so on. Like if we look at what happened with the data science trend, like it won't wane, but what will happen, I believe, with LLMs is there will be more, right? Like right now, I look today, there's 1,300 jobs on Glassdoor, open job positions that specifically require LLM skills. Some of them like a preference, but a lot of them is actually you need to know LLMs. You need to do this. You need to be doing engineering. You need to be doing scaling. You need to be doing data collection, whatever else. Managing an LLM team. 1,300 doesn't sound like a lot. And that's why the salaries are so high. But as time progresses, there'll be more candidates who know LLMs because people will learn. And also, there'll be more companies who will want LLMs. So the demand and the supply will increase, and eventually the salaries will taper down. That's my prediction. That we're not going to be seeing $600,000 salaries for an LLM engineer like 1 year from now. Maybe okay, 2 years from now. I think there'll be a more of a better equilibrium in the market for LLM jobs.
yeah, maybe. Yeah, I'm not sure I 100% agree. I guess because I think it ends up being like at the time that data scientists say there were only 1,500 of them,
Yeah.
there were probably some that were asking $500,000 or whatever, but there were also, it's probably more normal to be like 200,000 or 100,000. And as time has gone on, the number of data scientists out there has become so large that there's still like, I think the shape of the distribution is probably, I don't know if it's about the same, or there's probably, I think there's probably more people who are data scientists making those very large salaries than ever before, even though the demand and supply like would have been more, the supply would have been more constrained for sure 10,
Yeah,
12 years
yeah.
ago. But there has also been a lot of seniority developed, a lot of niches developed, and so I suspect that in terms of total number, there's more people commanding those kinds of like $500,000 or more salaries in data science than ever before.
Interesting, interesting. So in absolute terms, maybe you're right. But if we think in relative terms, like if you have LLM skills right now, you're much more well positioned than if you will have LLM skills 2 years from now. Like you will be, in relative terms, I think you'll be much more competitive.
So, your business wants an LLM to transform customer service. Well, you could iterate on disconnected platforms, struggle with the lifecycle of open source tools, or you could iterate freely without creating a single ticket. Register for a free 30-minute workshop and watch a RAG retrieval augmented generation powered system be built in record time using Kubeflow, MLflow, and Kserve, pre-built notebooks, and battle-tested machine learning tools, all in one place as part of HPE Ezmeral software and powered by Intel Xeon scalable processors. Head to hpe.com/Ezmeral/chat with your data to join this free cutting edge event. We've got the link in the show notes for easy access.
Yeah, yeah, it's definitely better to build those skills now. But I think people typically, once you kind of ratchet up to that kind of higher salary, I think it's kind of rare for it to come down. Instead, you'll develop more skills. You'll be even more on the cutting edge. You'll have LLMs plus some kind of specialized LLM skill that comes next that you
Yeah,
can
yeah,
add in, and you can be like, I've been publishing LLM
yeah,
papers since 2024.
yeah, 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 yeah.
And so, yeah, so you'll be this kind of like senior LLM leader by the time that comes around.
Especially if you listen to this podcast. John talks about LLMs a lot. Like I've been following, of course, I've been following. So if you want to be an LLM expert, make sure to subscribe. Subscribe to this podcast wherever you're listening to. Quite a lot of guests come on to talk about LLMs. I think
Yeah,
it's
I mean, we try to find the biggest and best guests out there, and we don't typically dictate what guests should be talking about. Uh, but the most interesting guests in the world, you bring in people from Berkeley or Stanford or other top labs, Google DeepMind. They're either directly or indirectly, typically right now, working on LLMs or generative AI in some way, and typically also getting their own startup going that's involved in some kind of generative AI startup as well on the side going. So yeah, it's definitely, there's a huge amount of opportunity here. It's because it's such a powerful technology, an unprecedentedly powerful technology. And so there's an abundance of opportunities for us to be making amazing applications, making a huge difference to people and to businesses. And so yeah, certainly it's been the topic of the year,
for sure.
in the year past in 2023.
For sure.
And yeah, wouldn't be surprised if we've got a lot of LLM episodes in 2024.
Yeah.
But this is a different episode because typically when I have guests on to talk about LLMs, they are going into detail on some specific technology related to LLMs that they have, some particular application. But here today, you're going to be doing a survey, and you're going to be, yeah, introducing the whole area to us from the ground up. And so, yeah, so I guess you've been working a ton on an LLM's course, right?
Yeah, yeah, for sure. It's it was funny. Like it was in September this year when we realized, okay, we've done like quite a big march forward with the cloud platform that we're building, and people are quite happy. We've got a lot of content in there. Let's take a break for a month and build this large language models A to Z course in line with our A to Z kind of like not franchise. What's it called? Like line of courses that we have, machine learning A to Z,
Yeah.
AI A to Z. We thought, okay, LLM A to Z. Take us a month. 4 months later, I'm only finishing up. There's 30 intuition tutorials in there. As usual, I do intuition. Adlan does the practical, and we're doing fine-tuning of an LLM to, he's doing fine-tuning of LLM to a medical data set, which is very exciting. I'm doing the theory of transformers from the ground up, GPT models, everything, LLMs. And there's like 30 tutorials. I counted yesterday, like 31 tutorials. It took me 4 months to put all together because like I had to scour the whole internet, read research papers. Of course, attention is all you need, research paper plus a lot of the other ones, blogs, videos, you name it, and get all these details and from like experts in the field, from I don't know, people who are just dabbling in it, blogs that were written a while ago, because transformers were introduced in 2017. So there's a lot of information out there on them. Um, and yeah, finally, I can with great confidence say that we're finishing up. Like this week, our plan is to finish it up on 31st December, and the course is available. It's exclusively available on the Super Data Science platform, not available anywhere else, not available on Udemy or anywhere else. So if you want to check it out, go to superdatascience.com/LLM course. Um, and I can confidently say that in my, like from what I've seen, I genuinely believe this is the best course on LLMs you can find out there. Yeah, so that's the course we've been working on. It's available. You can't buy it separately. You have to become a member at Super Data Science. But with that, you also get all access to all of our other courses, workshops, which in 2024 we're going to be doing regularly, at least once a month, maybe more often, on LLMs and other things, and other perks inside the membership.
Nice. So like workshops are like interactive?
Yeah. Workshop interactive. We're already doing them in our cloud platform. People love them, so we're going to be doing them in our community on Super Data Science.
Yeah. So when you say cloud platform, you mean like your cloud instruction platform, Cloud Wolf.
Yeah,
You've
Cloud
been
Wolf.
doing
Yeah, so
like
we have
yeah,
Cloud
yeah,
Wolf for people who want to learn cloud and get AWS certified, and we have superdatascience.com for anybody who wants to learn data science, machine learning, AI. But having said that, I'm here not to just promote the course. I'm here because I am fresh, like in terms of my knowledge. Like past 4 months, I've been doing LLMs. We're going to switch over back to creating cloud content in the next few weeks, and I wanted to really capture this knowledge inside a podcast and share with people. So my goal is that by the end of this episode, you will understand, as a listener, you'll understand the ins and outs of how a transformer model works. We'll be focusing on GPT models, which are decoder only models. And by the end of this episode, you will understand all of the components that are inside a GPT model / a transformer model, what LLMs are, and how they work on the inside. Like you've heard a lot of podcast episodes on this show, as John mentioned, about people talking about applications of LLMs or research and really cool things. Today is the opportunity to understand how it really all works on a technical level. So I'm very excited to share the insights today.
But before we dive into this, Kirill, is this something that should be scary or intimidating for people? Are LLMs like harder to learn than other kinds of concepts?
That's a great question. I would say that LLMs are not much harder than learning about neural networks, and if you understand concepts such as like backpropagation, um, even a gradient descent, like even if you don't know them yet, like LLMs are easier than that in my view because it's an architectural solution. It's a matter of understanding the building blocks that go into an LLM, and if you really know about our neural networks, it's going to be pretty straightforward. It's the hard part for me was spending the 4 months and putting everything together because there's no one source, or there wasn't until we've released this course. I don't believe there's this one source where you could get all of the information coherently in one place with all of the little details covered and nothing left. Like I'll give you an example. Like I thought 2 days ago, I thought, okay, I'm done with the course, almost done, just a few tutorials left. I'm just gonna revise everything I've learned over the past few months for the preparation for this podcast with John. And then, boom, like literally yesterday, I was sitting there reading another piece of information. I couldn't find any answers. So I was digging somewhere in Stack Exchange on AI, not even in the main thread, like in a chat inside Stack Exchange, where some researcher was answering somebody's question. And like I had an epiphany. And like the one of the biggest breakthroughs that happened in my learning of LLMs happened literally yesterday because it was so hidden and it's not obvious. It's not in the research paper. Some people who know how these things work, they assume you understand. Some people who don't know, in most cases, will probably miss this part, and we'll talk about it later. It's about training of an LLM, how it actually happens in within segment
Nice.
parallelization of training. So
Nice.
to answer your question, it's not hard if you have all the information, and I will do my best to present all of it here. Again, if you want to dive deeper, check out the course that Hadelin and I are releasing.
Nice. Yeah. LLMs A to Z available exclusively in the superdatascience.com platform. All right. Let's start with the basics of LLMs, Kirill.
Okay, all right, here we go. Super excited. So, the ingredients of an LLM, you first of all need a lot of data. You need like tons and tons of data, hence large language models. You need a transformer architecture, which is the core of ChatGPT, Claude by Anthropic. Like basically even Stable Diffusion, right? Like it's an image system, but it actually also has transformers in its core. You need pre-training. You need a lot of pre-training, and that's where your most of your compute time cost is going to go. That's the most expensive and time-consuming part of the large language model. Then you can also optionally have reinforcement learning with human feedback, and also optionally you can fine-tune the large language model on domain-specific data if you like. So those are like the 5 core ingredients of large language models, and of course, there's other variations, other additions to them. A brief history of large language models. By the way, this is not mine originally. This history overview is something I saw in a lecture on YouTube by Andrei Karpathy. We'll link to it in the show notes if you want to check it out. But in summary, in 2003, Yoshio Bengio and some other scientists published a paper called A Neural Probabilistic Language Model. This was one of the first attempts to model a language with a neural way. Then in 2014, Ilya Sutskever, who currently works at OpenAI, published a paper called Sec-to-Sec Learning with Neural Networks. The importance of this research paper was that it combined LSTM networks, 2 LSTM networks, into an encoder-decoder structure. So the LSTM networks were originally invented back in the 90s, I believe, by Hop, I forgot. It's a German scientist.
Is it Jürgen Schmidhuber?
Jürgen
Jürgen
Schmidhuber.
Schmidhuber.
Regan Schmidhuber was his supervisor. Yeah, this was Hopfganger or I forgot his name. So he was the student under Jürgen Schmidhuber. So, well, the two of them
I think
invented
it's Hochreiter.
Hochreiter. So my apologies for mispronouncing. So Hochreiter was a student of Schmidhuber. And by the way, it's really interesting to watch Schmidhuber's. I remember back from 2017 watching his YouTube when we were preparing artificial intelligence A to Z, watching some of his talks and comments on AI. Maybe it's changed, but back then it was very, very dark. It's got a very dark outlook on the impacts of AI, and even back then, like all the bells that people are ringing now in terms of the dangers of LLMs, and we're not going to go into detail on that. But he was already talking about the dangers of AI back then, and he's got a pretty dark outlook in my perspective. May have changed, or maybe other people have different perspectives. Anyway, so Ilya published this paper, and it was a first paper where 2 LSTMs were combined in the encoder and decoder structure. So basically, and this was for translation. So you take in the sentence, and an LSTM, if you need a refresh, is a type of recurrent neural network. You take a sentence you want to translate, you put it into this neural network one word at a time, and then this is the LSTM. Then at the end of this encoder LSTM, you have a vector which transfers all of that information to the decoder, which is another LSTM, and then the decoder now unravels it and makes the translation. That was the design. And I remember playing around with this in 2017 for our artificial intelligence A to Z course. And the big problem with that architecture, even though it was already showing some promise, two big problems with that architecture. First one is it has to take in the information sequentially. So it's very hard to parallelize, and you can't scale it easily for training. Second thing is that because you have this one vector, word vector or context text vector, whatever you want to call it, between the encoder and decoder, like there's one vector that connects the two. you're trying to squish all of this information into one vector and then pass it on to the next one. And so the longer your input, the harder it will be. Effectively, you're creating a bottleneck. And that's why LSTMs, they have a lot of merit, very eloquent solution to some of the problems there, with like the vanishing gradient and so on. But at the same time, they didn't go that far, mostly because of these two issues. And yeah, so that was in 2014. And again, in 2014, just around the same time, there's another paper by Dmitry Bogdanov, who published a paper called Neural Machine Translation by Jointly Learning to Align and Translate. And he introduced a concept on top of this architecture that, with the LSTMs, he introduced a concept of attention. Well, actually, he didn't call it attention. He was going to call it something else. But Yoshio Benjo was one of the co-authors on the paper as well. And he suggested the word attention. And so the way that this paper works is basically, it's like, okay, let's use this LSTM architecture, recurrent neural nets, for language modeling. But in addition to, in order to solve the bottleneck problem, we're going to now give this extra mechanism of attending to words. So allowing the neural network to remember certain characteristics, certain information about different words and store it separately so that it can then be used in the translation part or in the output part. And this was a really cool solution, or really cool way to address the bottleneck problem. So the way to think about it, and the way Dmitry Bogdanov explains this in an email reply to Andrei Karpathy. So Andrei Karpathy, when he saw that, he actually asked Dmitry Bogdanov how he came up with this idea, and he replied, and this is public on one of the YouTube videos by Andrei. The way he explained it is like Dmitry's first language isn't English, so he had to learn English. So imagine when you're learning to translate from English, or from your language to English, or the other way around. As a human, you're writing out this translated text. Let's say you have your language, like a paragraph, and you're writing out this paragraph in English. So you're writing it out, and like, let's say you're on the 7th word. Now for the 8th word, you don't just have it all in your head. You don't have the context, the whole meaning of your initial paragraph in your head. You look back. You look back and you look at different words. You like combine them again, revisit them, and then you translate the 8th word. And then for the 9th word again, it's not all in the head. So think about it as like, for machines, like we were thinking, oh, let's have in the LSTM paper by Ilya Sutskever, everything is in this one vector. It's like having the whole paragraph you want to translate just in your head and trying to translate it. Whereas the addition of attention is like in a human version, where you're looking back throughout while you're translating, you're looking back at the original text to help you translate each sequential word.
Empower your business with Profits of AI, the leading agency for AI and robotics experts. Whether you seek a captivating keynote speaker, a company workshop host, or even guidance in implementing AI seamlessly into your organization, Profits of AI connects you directly with the luminaries shaping the future of AI, such as Ben Goertzel and Nell Watson, both of whom have been phenomenal guests on this very podcast. Whether you are a large global enterprise or just beginning your AI journey, Profits of AI have a solution for you. Their speakers have graced the most prestigious stages around the world, and now you can head to profitsofai.com yourself to see their full roster, or to the show notes where we've got their contact link.
Makes perfect sense. It would bridge conceptually this kind of gap in capabilities between pre-attention. It would be a relatively easy task if it happened to be the case that you could kind of like one-to-one map from one language to another word by word.
Yeah.
Where you could just be like, the dog runs, and then you translate that into some other language, some target language, French or Russian or whatever, Chinese, and somehow it ends up being that it's still just the dog runs, exactly 3 words in exactly that order. Then probably without attention, translation would be easy. But attention, as you're saying, it allows you to consider more than just this linear sequence. You are considering all of the context, potentially not just before a given next word, but also context after it, in order to pick the 7th word, the 8th word, the 9th word appropriately.
Exactly. Yeah, that's right. And different languages have different styles and like different rules, and it's much more complex than just translating word by word. And interesting point is that we're talking about translation here is because it's the most obvious problem for like dummy or practice or training problem or challenge to solve with a machine solution. Like ChatGPT doesn't. It's not, the design is not for translation, right? It's for prompt engineering or prompts and answers and text generation, right? But like originally, the way this field evolved is all these papers, they're focused on translating because that's kind of like the obvious challenge or obvious problem you can solve. And speaking of this, the next paper, the final one that we're going to mention today, which was published in 2017 by a whole team at Google. I believe it was 8 researchers at Google. Is called "Attention is All You Need," and again, it was focused on translation, and that's the paper that introduced transformers. So a cool a piece of trivia is that transformers were originally designed as a translation mechanism because of all this history, but later, only now, well, afterwards, they were adapted to like BERT models, GPT models, and for GPT models for text generation. And so what's very interesting and phenomenal about this paper, "Attention is All You Need," it's like it's in the name. What they did is they took this LSTM structure, encoder, decoder, plus the attention that was introduced by Dmitry. And then they're like, okay, let's throw out the LSTM. Let's just keep the attention part. Why do we even need this? So the Dmitry's paper in 2014 solved the bottleneck problem or addressed the bottleneck problem, but then they still had that sequential processing problem, that it wasn't easy to parallelize. But when you throw out the LSTM and now you only have the attention part, now you don't have a bottleneck problem and you don't have the step-by-step sequential input processing and generation problem. And all of a sudden you open a whole world of possibilities as long as you can pull it off, as long as you can create a architecture that works based on just attention. That's exactly what this team at Google did. And this was back in 2017. As you can see, you correctly mentioned, John, like transformers have been around for a while, but it took 5 years for it to really break through in the form of ChatGPT and gain popularization. And now it's all over the place. So so that's where we're at, and that's the paper we're going to be going through today. It's going to be a very interesting challenge because it's an interesting challenge for me to put together like an explanation of how a transformer works without any visual aid. If you are in front of your computer, feel free to open up this paper. It's called "Attention is All You Need." You can download an archive and open up the diagram of the transformer. You can follow along. You'll notice that I'm simplifying things and leaving out a few items that are not important, but we'll talk about the most important things. If you're not in front of a computer, no worries. Whether you're driving, running, cycling, whatever, relaxing on the couch, I believe I've come up with a method that will help you visualize it in your mind. Just be careful if you're driving. Of course, don't get too carried away, please.
Nice. And I think a key thing here to mention is you already touched on it there a little bit, but I'll dig into it in more detail. Is that even though this key paper, "Attention is All You Need," from that team at Google is from 2017, the concepts underlying large language models today, in terms of neural network architectures, are the same. So 7 years later, it's just been a matter of scaling up in terms of sizes of the training data available for training these LLMs, and then how many of these things called attention heads, which I'm sure you'll get into later, but the number of attention heads in the LLM gets bigger and bigger. And also context windows have been getting bigger. So it's basically just size. It's just a matter of scaling up. But fundamentally, the neural network architecture is the same. It's just bigger. And so
Absolutely.
that's why it makes sense to dig into in so much detail this one particular paper from 7 years
Absolutely.
ago.
In addition to what you said as well, I was watching a video by Andrew Karpathy, and he pointed out that not just the architecture is the same, but even a lot of the parameters or hyperparameters are like the ones they picked in the paper. They haven't been any super major breakthroughs or super major changes. Like I don't know, the number of like the embedding size of the vectors, or how they did not batch normalization but layer normalization. Something we won't be talking about is like an additional step, or these residual connections. Is like only a very few improvements have happened over the past 7 years. Most of the stuff that like is we're using these days, of course, to what we know, there's a lot of proprietary things with OpenAI, as Elon Musk called it, becoming the super closed AI for profit organization. Like we don't know exactly how they're structured, but most of the things that were proposed in this paper still work to this day and haven't been um, outperformed by any significant modifications that have happened since.
All right, so let's get into your visual of transformers from the Attention is All You Need paper. And by the way, we will have links to all of these papers that were mentioned in the show
For
notes.
sure,
So
for
they'll be
sure,
there
yeah.
in one place. If you're driving, don't visualize too hard. Keep an eye on it.
Yeah, and if you find, I wanted to say, if you find parts of this like too complex, like especially when we're talking about that tension mechanism, it can become a little bit technical. Feel free to skip through like a few minutes and get to the rest, because um, later on, after the technical stuff, there'll be more very important non-technical aspects as well. And in addition to that caveat, I wanted to mention a few other ones before we dive into the components of a transformer. The first one is a transformer has two parts to it. It has an encoder and a decoder. We're going to be talking about just a decoder. Why is that? Because a GPT model, with like ChatGPT, for example, is a decoder only model. This is a good piece of trivia. It's not obvious when you think about it. Like, yes, ChatGPT uses a transformer, but it doesn't use the full transformer. You throw out the encoder part, you only use the decoder. Whereas another piece of trivia, if you look at a BERT model, you only use the encoder part, you throw out the decoder part. So, but we're going to be looking at just the decoder part of a transformer. Another caveat, GPT
I can,
stands. Yeah, go ahead.
if you don't mind, Kirill, I'll add to give a bit of context on why you would use just an encoder or use just a decoder.
Yeah.
So a decoder only model like the GPT series, it is designed primarily to be generating text. So
Mhm.
it's this generation, which is the decoding part. So it's kind of easy to remember. That decoder part of the transformer. When would you use it? It's when you want a model that is optimized for outputting, generating like a generative AI model, like a chatbot,
Mhm.
ChatGPT. So the
For
GPT
sure.
series architectures, decoder only. The inverse, encoder only, ends up being really helpful when you're not doing a generative task. So when you want to use the information in some other way, so maybe you're building like a classifier or some other kind of machine learning model, maybe like a ranking algorithm, like you're going to convert all of your documents into some abstract space. You'll use the encoder part of the transformer to do that encoding. And so you don't need the decoder. You're just concerned about encoding in those cases. And yeah, BERT is definitely the most famous example of a BERT, like from Sesame Street. There's lots
Yes.
of in some of the early. You didn't talk about these particular papers, but there were a bunch of early attention and transformer related papers where there was like Elmo, and then there was
Oh, yes.
BERT,
Yes.
and so yeah, that was a bit of a funny trend. Now some years ago.
Yeah.
Anyway, sorry, I interrupted you.
Sure.
So yeah, encoder decoder, and then you were on to the next thing.
Yeah, the next thing was another just so we're on the same page, another piece of trivia. GPT stands for generative pre-trained transformer, hence that transformer because it's used in GPT models. And one final thing I wanted to note is that even though basically in our course that we released, we cover everything from encoder to decoder, all the steps, everything completely. But for simplicity's sake and to keep things concise, in this podcast, we'll focus on the decoder only, and also because that's what's relevant to GPT models. All right, cool. So let's get straight into it. I'm super pumped about this. So the attention is all you need paper has a diagram. Obviously, we're going to have to visualize this. The best way, we're going to simplify some things. The best way to think about it is imagine five boxes stacked on top of each other, all a blank, right? We're going to be filling them in. And they're connected from the bottom box to the next box up with an arrow, and then to the next box up with an arrow, and so on. So basically, that's the architecture of the transformer. It starts from the bottom and goes up through these boxes. And we're going to now
It,
fill in
it
these blanks.
it's like a 5-story apartment building. You start on
Yeah.
the ground floor, and then you move to the second floor, then to the third floor, all the way up.
Yeah, if you're in case you're a 5-year-old listening to this, John has got you covered with his 5-story analogy. I'm pretty sure our audience can visualize 5 boxes. But thanks. That's a good addition. All right. So, yes, 5 stories. Starting with the first floor. Or well, how do you do it in Canada? In Australia, it's ground floor and then it's first floor.
As we often discuss on air with guests, deep learning is the specific technique behind nearly all of the latest AI and machine learning capabilities. If you've been eager to learn exactly how deep learning works, my book, Deep Learning Illustrated, is the perfect place to start. Physical copies of Deep Learning Illustrated are available in 7 languages, but you can also access it digitally via the O'Reilly Learning Platform. Within O'Reilly, you'll find not only my book, but also more than 18 hours of corresponding video tutorials if video's your preferred mode of learning. If you don't already have access to O'Reilly via your employer or school, you can use our code SDSPOD23 to get a free 30-day trial. That's SDSPOD23. We've got a link in the show notes.
So Canada and the US, there's no like floor 0. So the first floor is the ground floor. But yeah,
Okay.
in Europe, because in Australia, what side of the road do you guys drive on in Australia?
On the UK side of the road, on the left.
On the UK side. So you drive on the left side of the road and you have a floor 0. Yeah.
Floor G, yeah. All right. For simplicity's sake, we'll use the US method. So yeah.
It really makes before we go into that, it makes a lot of sense to have a floor 0. I know we're going to go with floor 1 because
Yeah.
it does definitely make a lot of sense. But in terms of just the way that numbers work,
Yeah.
you shouldn't just go from 1 to -1. You've skipped an integer.
Yeah. That's a good point.
So it makes a lot of sense. Anyway,
Yeah, but in some countries, like due to I believe like beliefs or superstitions, they omit certain floors or they use floors. For example, in China, the number 8 is very popular. So I was in one building where like I looked at the elevator buttons and it was like I don't remember like of 8th floor because my friends were staying. They lived on like the 19th or 18th floor or something. So it goes like 16, 17, 18A, 18B, 18C, 18D, 18E, 19, 20.
Yeah,
Yeah,
I wonder if they skip 13 in China. They skip 13 in my building in New York, my residential
yeah.
building, because they'd have to charge less rent.
Or
But
when you sell it, right? When as a developer, when
yeah,
you're selling it, you're gonna have
yeah,
to convince buyers or sell it for less.
yeah. But beware, all you 14 people, you're very unlucky floor. You just don't know
Well, it might be 12 people if you add the ground floor at the
it.
bottom.
Yeah. All right. So
Anyway,
anyway, so we're gonna go with the American system for this analogy. So okay,
yeah,
we're on level 1, which is also
level 1.
confusingly, perhaps for our European and Australian listeners, the ground
Level 1.
floor.
So let's imagine you have level 1 is called input embedding. So you have a whole sentence or vector or so of words you want to give them to a machine, a transformer. Obviously, machines can't really work with um, words. They need to work with numbers. So we want to convert each one of these words. Well, when I say words, on this, if you've been listening to this podcast, you've heard John many times talk about tokens, and that's what LLMs work with tokens. They're not necessarily full words. They're maybe half words, like parts of words, and but for the sake of this podcast, I'm going to be using tokens and words interchangeably. So you have this series of
Really
go ahead.
quickly, for a great intro episode for people who want to dig into those subwords, specifically episode number 626 is all about subword tokenization. But yeah.
Fantastic. Yeah, check that one out. It's quite an important topic. So we're going to be talking about words and subwords and tokens all the same, because that's not the focus of this episode. So you have these words. Now, for each word, you're going to need to create a vector, and not just a random vector, but a context-rich vector. And I'll give you an example. So, John, let's do a quick riddle. Imagine this equation. If you take king, the concept
Yeah.
of the word king. You know this one, right?
Yeah.
You subtract the concept of the word man and you add the concept of the word woman, right? Like, what is your answer? King minus man plus woman. What are you going to get?
Let me puzzle on this for a moment. Maybe, is it princess? I feel like I'm in the right neighborhood.
No, it's not princess.
It's Elizabeth.
Almost. It's a queen. It's a queen. So basically, if you think about it, like if you take the characteristics that or the features of the essence of the word king, like every word in the English language has an essence, which can be described with certain features. Like for example, a king is wealthy, right? Like generally, kings on average are pretty wealthy. A king is pretty authoritative, right? They can dictate to people what they do in their kingdom, and so
They
they
wear
are in charge of a
crowns.
kingdom. Yes, like they are royal, right? But they're not just royal; they are in charge of the kingdom. Like a prince is royal, but a king is royal and is in charge. He has authority over the kingdom. Um, and things like that. So you can describe words with different features. And if you take the essence of the word king and you subtract the essence of the word man and you add the essence of the word woman, naturally, intuitively, you get the word queen, even though we're doing arithmetic with words and not numbers. And this kind of like hints towards the fact that you can actually describe a word with lots of different features and then do arithmetic using those features. And so in the sense of transformers, what we use are vectors, they're called embedding vectors, and they have 512 dimensions. So quite a lot of features, 512 to be precise, are
And that's specific to this attention is all you need paper. That number of dimensions is arbitrary. It could be
yes, you can change it. Make
smaller.
it
Yeah,
256, make it 10 million if you want, but it'll obviously impact.
yeah.
Um,
Compute efficiency versus so the more dimensions you add, the more numbers you need to represent the location of a word in this embedding space. So if you have 512 dimensions versus 256, it's twice as much information you need. However, that could be worth it. It could make more nuance. And so as you say, as you increase the number of dimensions towards infinity, the improvement in quality of your embeddings for whatever downstream application you have doesn't get better at some point. And
yeah,
so
yeah,
you need to, decide, all right,
it's a
let's just cut
trade-off.
it off here at 512. Yeah, yeah.
And we're not going to go into detail on how this is done because there's solutions on this. You can look up bag of words model. You can look up the n-gram model. You can, for example, you could just use already an existing embedding for all the words. Like there's ways of doing it. Just the main takeaway from this is that the vectors that are created in this first box, the vector embedding of the words, they're not just random vectors. They are vectors that capture the semantic meaning of the word. We'll be talking about, because this is language, we'll be talking about different types of meaning. And they capture semantic. Semantic meaning is the dictionary meaning. So if you open up the dictionary, it'll describe what an orange is, what an apple is, what a horse is, what an ocean is. And these vectors capture them. So in your vector space, what you'll have is not just a random series of vectors. That's pretty easy to create, just a random series of vectors, unique vectors for words. But you'll actually have vectors for every single word in the English language, which can range between 50,000 words to 600,000 or a million words, depends on how you look. But like let's say 200,000 words in the English vocabulary. So for each one, you'll have a unique vector, but not just a random one. They will be capturing semantic meaning, and that implies that words that are similar will be close to each other. So like an apple will be close to an orange, close to a banana, whereas I don't know, like a car will be somewhere else in this vector space in a different location because they're not that similar. Like the adjective good and great and excellent will be close to each other. The adjectives bad and terrible will be close to each other. So you just imagine this multi-dimensional 512 dimensional vector space, which is impossible to imagine. But in this space, similar vectors, vectors representing similar words are going to be similar to each other. So that's box one, right? We've converted our text into every single word of our input now has its own semantic meaning or embedded vector which captures semantic meaning. Good. Moving on to box two. Okay. So box two is called positional encoding. Why is positional encoding important? What is it? Let's look at this example. Horses eat apples, right? It's a grammatically valid English sentence. It makes total sense, means something. Now let's take the same words and rearrange them. Apples eat horses. It's a grammatically correct English sentence. It follows all the rules. It has exactly the same words, but it means something completely different, right? And in fact, it's nonsensical. Apples don't eat horses. So that just illustrates that word order.
You just haven't done enough LSD.
Yeah, in some weird dreams, maybe.
Carry on.
Yes, or for some people it might make a lot of sense. Anyways, but the point is that word order in a language is important, and it can significantly affect meaning. When we were talking about, or when the state of the art for language processing were recurrent neural networks and LSTMs, that wasn't a problem because they inherently preserve word order. They take the words in sequentially. Whereas transformers have a major breakthrough in the sense that they take the input in parallel, so they're much faster. But at the same time, that creates the disadvantage that they don't inherently preserve word order. And so, therefore, in order to correctly convey the meaning of a sentence into a transformer model, you have to have positional encoding. Again, this is one of those things that we're not going to dive into. There's many ways of achieving positional encoding. The one they use in the Attention's All You Need paper is very elegant. It uses cosine and sine functions. It's deterministic for each position in the input sentence. But in a nutshell, what happens is, to each one of these vectors that we have for our words, so like we have a word, let's say it has a sentence, it has, or the input, let's say it has 50 words, so that means there's 50 positions. To each one of the vectors that we've created, the embedding vectors, we add a small number which represents the position of that word in the sentence, right? Or it's not a small number, like a small vector. We add to each one of those vectors, we add another small vector which represents the position of that word in the sentence. And that is a mechanic. So we're just creating the environment for the transformer during training to leverage this, right? So our job is to encode the positions into these vectors. The transformer will learn how to use that mechanism that we're giving to it through this approach. So that's what box number 2 is: positional encoding. All good, John? Anything to add?
Nice. Yeah, I'm keeping track here. So floor 1, input embeddings, where we're getting each of our words put into a vector space, a location in the vector space. And then when we go up to the second floor, the floor you just finished describing, we've got the positional encodings. And then, yeah, now we're going to go up to floor 3.
All right. Floor 3 is the middle and is the most important part. This is the attention mechanism, and that is the heart of the transformer. That's like what's most revolutionary about this model, and that really enables a lot of what we're seeing, a lot of this text generation. Like if you think back to LSTMs and when they were generating text, like a lot of the time was nonsensical. There was no coherency to it, cohesion. I always get confused between the two. Whereas transformers, it's pretty like a lot of the time indistinguishable from human text, and the main reason for this is this attention mechanism. So we're going to talk about the attention mechanism, and before we do, I'll give another example. So let's think about this sentence: the dog did not cross the street because it was too tired. Right? You know this one, John?
No, actually.
Okay, so the dog did not cross the street because it was too tired. Which what does the word it mean? Which noun does it refer to in this sentence?
Right. The dog, of course.
The dog, obviously, because the dog, it was too tired. But now let's change one little thing, one word about the sentence at the very end. The dog did not cross the street because it was too wide. Which word does the word it mean now? What does the word it mean now?
Nice. Now it's the street. That was a great
It's
example.
the street. Right,
Nice.
right. This is actually from one of the TensorFlow or Google libraries visualizing transformers, and they use, I think, the animal did not cross the street because it was too wide, too tired or too wide. So by changing one word at the very end of the sentence, all after those nouns, after the word in question, the word it, by changing one word, we can change the meaning of a preceding word, of the word it in this case. So in one case, it means dog. In one case, when it's too tired. In one case, it means street when it's too wide. And that shows us that there's not just semantic meaning behind words, there's also contextual meaning. There's lots of types of meaning. They can be sarcastic meaning, they can be emotional meaning, there's lots of different meanings in linguistics. But the two main ones that we're focusing about here is semantic meaning. We already have that in our vector embeddings. But now there's a new kind of meaning that we don't have captured in our vectors, and that is contextual meaning. And that depends on the words around the word. It depends on the whole sentence or the whole paragraph or the whole text that we're processing. So contextual meaning is also important, and it can alter the meaning of the word that we're looking at. And so the goal of the attention mechanism is to create new vectors. So we have vectors that embed semantic meaning that then have positional coding. Now we want to enhance them even further and create vectors that can contain contextual meaning. And that's what the attention mechanism addresses. I'm going to go through how the attention mechanism works. It's going to be a bit more technical than everything else we've had so far in the podcast. It'll be the most technical part of this podcast, of this episode. I'll do my best to simplify it as much as I can. But if you find it a bit too technical, maybe skip forward a bit and come back to it when you're in front of a computer and you can open up the attention you need research paper. Or, again, you can always come to our course where we dive into these things over 30 tutorials. But let's do our best to dive into it. We're going to be talking about performing operations with vectors. And there's three ways to think about it. The most mathematically correct way is to think about them as linear matrix operations, right? So you have a vector, you apply a linear matrix operation to it, and then you get a resulting vector. So when we say we want to create a vector from this vector, that means we're just applying a matrix operation. Second way to think about it is neural network mentality or approach. Is you think of a vector as an input layer into an input series of nodes, let's say 512 nodes, and that's the input to a fully connected layer. And the output is, if you want a 512 dimensional vector, there's 512 nodes. You want a bigger, smaller vector, more nodes. And basically, so both layers are fully interconnected, and there is no activation function. That's basically how we modify or create a new vector from an old vector, if you think about it from a neural networks perspective. And the final way is the most simplistic way to think about it is if you're not very good with matrix operations, if you're not good with neural networks, you just want to visualize it somehow. It's like a vector has 512 features. So you want to create a new vector also, let's say with 512 features. Well, the first feature of the new vector will be a weighted sum of all of the features of the original vector. The second feature of the new vector will be a weighted sum of all of the features of the original vector, and so on. So it's always a weighted sum. The weights are obviously random and different, and they are adjusted through training through a process called backpropagation. And the neural network will learn, or transformer will learn, how to improve those weights. Whether you think about it as a matrix operation, a fully connected layer, or the simplistic approach, these weights will be adjusted so that the transformer can perform the task we want it to perform in the most correct way, in the desired way. Okay, so that's a caveat about vectors. And so let's dive into this attention mechanism. The way it works is we have these vectors. So let's say we're going to look at a sentence. Apples are a type of delicious blank, right? So we want to predict the next word. So we have 6 words. Apples are a type of delicious, and we want to predict the 7th word, which it's probably going to be fruit, right? But it's a blank at the moment. We want to predict what that is. And in order to do that prediction, we're going to enrich our vectors with contextual meaning. So we're going to look, as an example, this process that I'm going to describe is done for each one of the words, each one of the 6 words that we have. The attention mechanism is going to be applied. But we're going to look at just one word just to keep it simple, and just going to pick one word as an example, and then just assume that the same thing happens for the rest of the words. So for each one of these words, we from the original vectors that we had, the vectors with the embedded vectors with the positional coding, we're going to create 3 new vectors for each word. There's going to be a Q vector called the query vector, a K vector called the key vector, and a V vector called the value vector. So Q, K, and V. So we'll have a QKV vector for the word apples, QKV vector for the word are, and so on, the QKV vector for the word delicious. Now, the Q vector, and they're all created whichever way you want to think about it, whether it's a matrix operation or a neural network, simple way that we just described. There's three ways. Like pick one of those and just think of it. That's how they create. So there's basically a matrix of weights for creating Q vectors in this attention mechanism. There's a matrix of weights for creating Q vectors, a matrix of weights for creating the K vectors, and a matrix of weights for creating the V vectors. Three separate matrices that all need to be learned through training. Now, the Q vector is a vector which is saying what this word wants to, what this word is interested in. So the word delicious has its Q vector, and the Q vector of the word delicious is is a manifestation of what this word delicious wants to attend to. When this mechanism, attention mechanism, is trained and it's up and running, the word delicious will be looking through the rest of the words in the sentence, and it'll be using its Q vector to communicate. I'm looking for this. I'm looking for this concept. Do you have this concept? Do you have this concept? Do you have this concept?
So on floor one, when we had the word delicious,
Yeah.
that word, the word delicious just has a location in our vector space,
Yes.
and that word delicious is the same no matter what. Like its meaning is the same as root to that. But by the time we get to floor three here, and we have this attention mechanism, these Q, K, and V vectors, that word delicious that you're referring to, you're not referring to that in the abstract. You're talking about a specific occurrence of delicious in a specific sentence, in a
Yes.
specific, yeah. And so
Good point. Yes.
so it has like way more, yeah, these Q, K, and V vectors reflect all of the extra context that deliciousness has. So going back to the it thing that you were saying, these K, Q, and V vectors would allow us to be able to determine that it is referring to the dog or it is referring to the road. Whereas in
Exactly.
level one, it is just
Yeah.
it.
Yeah, exactly. So the Q vector for in that example, the Q vector for the word it is going to be signaling or explaining to the rest, is going to contain information about what that word it is looking for, right? So in one case, it'll be looking for an animal or like a living noun or like an actor. In another case, it'll be looking something, an obstacle, a street or something like that. Like it's obviously not going to be humanly intelligible because this is all going to be trained through backpropagation and lots of iterations in many epochs. But like you can think about it that way. There's something like each word needs some information about the context of this sentence that we're specifically talking about in order to to then become context enriched. And in our example, apples are a type of delicious blank. The word delicious is looking for certain things. And what it's looking for is going to be, we want the transformer to put that into the Q vector. So that's the Q vector for delicious. Next, every word, as we discussed, every word will have the K vectors. Now we're going to talk the QK and all three vectors. Now the K vector, right? So the K vector is like an indexing mechanism. It tells us what the vector contains. So the V vector will have the value, so the thing of interest. So each word will have something of interest that it can give to other words for their context, and that is stored in the vector V. Whereas the K vector is going to be communicating what is stored in this V vector. So each word will have a K vector, like the word apples will have a K vector. The word R will have a K vector. A will have a K vector. Type will have a K. Each one of them will have its own K vector. And now what's going to happen is we're going to compare. Remember, we're doing this attention. We're doing this for the word delicious. So the Q vector of the word delicious is going to be compared, and I'll explain what that means in a second. It'll be compared to each one of the K vectors of all of the words in the sentence, including itself. So the Q vector for delicious, so let's say I'm the word delicious. I'm looking for certain information. And that's what I'm looking for is described in the Q vector. Now I'm going to go take that Q vector, or the transformer is going to take that Q vector, and is going to compare it to the K vector of the word apples. If those vectors are aligned, that means apples has what I'm looking for, and I need to take the V value from apples and include it in my context. If those vectors are not aligned, then apples is completely irrelevant to what I'm looking for, and I should disregard whatever apples has in the V vector. Then I'm going to go to the next word, R. R is a plural verb. maybe it has some meaning that's relevant to the word to the word delicious that it's looking for. So the Q vector for the word delicious is going to be compared to the word to the K vector for the word R. If they are aligned, then yes, that the value inside the V vector of the word R is important for the context of the word delicious and should be taken into account. If they're not aligned, it should be disregarded. That value is not important to the context. And that process keeps happening, including with itself. So the Q vector for delicious will be compared to the K vector for delicious. If they are aligned, that means whatever value is inside the V vector for delicious is important to the context of the word delicious. If they're not aligned, that means it's not important. It should be disregarded. So that's how QK and V work. We'll talk about the mathematics of how this actually is implemented just now. But I just wanted to check, like, how did that sound, John?
Yeah, pretty good for I think it's about as well as you could without visuals, like you say. It's kind of it's a little bit tricky to keep all these things straight, but I mean fundamentally for any given term, any given word in a sentence, so like your sentence, apples are a type of delicious blank. Um, yeah, at each of those words, we've got the Q vector, the K vector, the V vector, and together that information allows us to map positions and context together to effectively attend to these words and understand them in context and allow us to predict what a good final word is at the end of the sentence. Apples are a type of delicious blank.
Yep. Yeah, exactly. And so that is achieved. The word of interest, in our case, delicious, you take the Q vector. And then for each other word in the sentence, including itself, you look at the K vectors and the V vectors. So you compare Q and K. And if they are aligned, then you take the V vector as part of your context. If they're not aligned, you don't. So how is this achieved mathematically? Well, it's quite an elegant, straightforward solution. You take the dot product of the Q vector for the word delicious and the K vector of whatever other word you're looking at. So let's say delicious and apples, right? So you take the Q vector of delicious, you take the K vector of apples, and you calculate the dot product. In case you need a refresher, dot product is basically the multiplication. You take the absolute value of each one of these vectors, you multiply those two absolute values, and then you multiply it by the cosine between those two vectors. If two vectors are perpendicular, then their cosine is going to be 0, and so their dot product is going to be 0. And if they are aligned, if they're pointing in somewhat the same direction, then their dot product is going to be non-zero. And the more they're aligned, the more they're pointing in the same direction, the higher their dot product will be. So that kind of reflects the logic that we just described of how we want the alignment of vectors. And the interesting thing is that we're operating in a 512 dimensional space. And in a 512 dimensional space, two vectors are always going to be perpendicular unless they share a projection into at least one of the dimensions. But because there's so many dimensions, the chances are that most vectors are going to be perpendicular. And so that gives our transformer a lot of room for maneuvering to keep a lot of vectors as 0 during as a result of the training. A lot of the dot products are going to be 0, except for the ones that really matter. So in the case of delicious, we want for the word delicious, we want as much context as possible because we're going to be predicting the next word. So obviously we need something from the word apples because, if we had, I don't know, like cucumbers instead of apples, then it would be cucumbers are a type of delicious vegetable, not fruit. So obviously we need context about apples in there. So that vector, that dot product has to be non-zero. And the transformer will have to learn that over training to set up the matrices. Remember we talked about the Q matrix, the K matrix, and the V matrix. It will have to learn to set up those matrices in such a way that in this particular sentence, the dot product of the Q vector for delicious and the K vector for apples is going to be non-zero, so that then we can extract the context from the word apples for the word delicious. So the dot products are going to be calculated in that way for each one of these combinations, the Q of delicious and then the K of each one of those words. So, and as a result, we're going to have 6 different dot products. Some of them are going to be very low, close to 0 or 0. Some of them are going to be high. For example, like in the case of apples, it should be quite high. Now we have these dot products. What we're going to do next is we're going to put them through a softmax function. Just as a quick refresher, softmax effectively takes the exponent of a value and then divides by the sum of the exponents of all of these 6 values in this case. So basically, it will give us a probability distribution. And we'll have these 6 elements in this probability distribution. So, for example, in the case of apples, it might be like 80% are like maybe 5% A type of maybe like 0%, whatever. So we get these probability distribution, and we'll use them as weights. And we'll use them as weights for the V vectors of the associated words. So, for example, in the case of apples, if the dot product of apples and delicious vectors, and then the softmax after it's applied, if that results in like 80% or like a 0.8, then we're going to take that as the weight of the vector V for Apple. So basically, we're going to take a weighted sum of the V vectors, and the weighting is going to be the softmax of the dot products of the Q for the word in question, delicious, and the K of each vector. So those will be our weights, what we get from the softmax, and we're going to be taking a weighted sum of the V vectors. Because the V vectors, as we discussed, they contain what that word is bringing to the table, like what that word is offering to other words as context, right? So in the case of delicious, we want the context from apples. We don't care about the context from A, R, A, of. We care about the context from type, and all of that will come as a result of basically um, it will be evident in the transformer after the training, after lots and lots of training, which we'll talk about later on. We'll talk about training. After lots and lots of training, we'll get a result where this contextual vector that we're creating as a weighted sum for the word delicious, it will have the right context from the right words that matter in this sentence. And that's a weighted sum of these V vectors. As you can see, it's a very elegant solution, very elegant mathematical solution to the logical problem that we had at the start.
Got a bit of a dumb question here, Kirill, but so everything that you're describing here, these Q, K, and V vectors, they're helpful for allowing us to attend to the words that we already have
Yeah.
in our sentence. And in particular, for these kinds of generative decoder only approaches, I think it's always the case that we're only looking back because we're trying to predict what the next token. It's a
Yeah.
so-called auto-regressive model where we're predicting the next
Yeah.
token, predicting the next word, which will mean that we're only ever looking back. So we have these vectors, these Q, K, and V vectors for some number of words looking back, whatever our size of our context window, which like with Claude 2 from Anthropic, it's like hundreds of thousands of tokens now in the context window. And so so we have these K, Q, and V vectors for all these historical tokens. But how does that relate? And maybe this is what you're going to get to. Oh, this is totally what we're going to get to next. Oh, yeah. Perfect. Perfect.
Tell
Perfect.
me.
Perfect. I bet that's where we're going to go with this is that ultimately, I guess what we're getting with all of these vectors for all of the preceding tokens, all the preceding words, this is going to allow us to predict what a good final word in the sentence. Apples are a type of delicious blank, right? Is that what, when we get to floor 5, we'll finally be able to have a prediction of what that word should be?
Yes, exactly.
Okay.
But
Okay.
you
Sweet.
made a very, very good question. You asked a very good question about um, like not looking forward, not looking ahead. And I want to put a pin in that because I deliberately omitted talking about masking in this explanation of tension. We will introduce masking later on in this tutorial. In this
It is the
episode.
tutorial episode of the podcast for sure.
Effectively, yeah. So in this episode, we'll later on introduce masking, but for now, let's put a pin in that and let's just assume that this whole process is done equally for all of these vectors. Although you are right, like when we're creating a context-rich vector, so this process, what I described, was creating a context-rich vector for the word delicious. So that weighted sum of those v vectors that we just got to, that'll be the context-rich vector for the word delicious. Same thing will be done for the word apple. Same thing will be done for the word R. So we'll end up with six separate context-rich vectors, one for each word. And John made an absolutely correct comment that, for example, the context-rich vector for the word type, which is the 4th word in our sentence, we'll have to we will have to have a mechanism for it not to be able to look forward. So it's not going to see the fifth word of, and it won't see the sixth word delicious. But we'll talk about that in a bit. So for now, let's just imagine that for each one of these for each one of these words, 6 words, we have a context-rich vector. Great. So that's the end of floor 3 or box 3. Now we're moving on to next floor 4. And things are going to get easier from here. So in floor 4, we have a straightforward feedforward neural network. And why do we need that in there? It's a 2-layer feedforward neural network. So you have these context-rich vectors. They go into a fully connected layer with an activated function. So they're 512 dimensional vectors. They go into a fully connected layer. I think it's a 2048 dimensional hidden layer. And then after that, they go back through another fully connected layer without an activation function this time. They go into the output layer. So basically two fully connected layers, or 2 layers. Yeah, fully connected layers. The first one has an activation function. That's the point of the feedforward neural network. First one, it adds more weights and biases, basically adds more parameters to the model, so to increase its learning capacity. And so it can model more complex relationships. And it also adds an activation function. So remember, up until this point, we haven't had any activation functions. We've only had linear transformations, matrix operations without any activation functions. Because that's how the transformer is structured. This is the first time in the neural network we're adding activation functions. So this will help it learn even better and more complex non-linear relationships in the data, in the linguistics. And another thing to note, very important, this is not like obvious if you're learning transformers for the first time. This feed-forward neural network is applied independently to each one of the vectors. So we have 6 context-rich vectors that we've created, and they go through this neural network independent. They go in parallel, of course, but they're not mixed and matched inside this network. The only time inside a transformer that vectors get to somewhat interact with each other is in the attention mechanism, where the vectors can look up these v values from each other using the QK indexing mechanism. Apart from that, everything is completely separate. So each one of these 6 vectors goes through the feedforward neural network and comes out on the other side even more enriched. Like their context enrichment hasn't changed because that was in the attention mechanism, but now they've had they've gone through a feedforward neural network with more weights, with some activation functions. So they're even more enhanced, even more enhanced vectors.
And
So
provides
that's
more flexibility.
Flexibility for what?
In the whole thing that we're trying to accomplish, like by having
Oh yes,
a
learning
feed-forward
flexibility.
neural network, yeah, like by having a feed-forward neural network anywhere when we're trying to map X to Y, a feed-forward neural network is always just going to allow you to have some kinds of subtleties be handled, some kind of flexibility in learning that otherwise might not be possible. So it's cool. Yeah, makes a lot of
Yep,
sense
for
to have
sure.
that in there.
Okay, floor 5, the final floor, right? So what you have in floor 5 is, so in the feed-forward neural network, we had a 512 dimensional vector go through the first fully connected layer of activation function. You get, in the paper, they say they have a 2048 dimensional, so it increases the dimensionality, and then the second fully connected layer reduces the dimensionality back to 512. So as an output of the 4th floor or 4th level, and as the input of the 5th level, we have we're back to a 512 dimensional vector for each word. There's 6 of them in our sentence. Now, what we want to map that to predict the next word. So we need that to map that to the vocabulary, to our vocabulary, which, like in the English language, let's say 200,000 words. So in the fifth level, in the fifth and final level, we have a linear transformation plus a softmax function. The linear transformation is designed to map the output that we have so far, the 512 dimensional vector, to 200,000 words, to 200,000 nodes. So it takes it's a neural network layer that has 512 in the input, no activation function, and it maps it to a 512 fully connected layer, maps it to a 200,000 layer with 200,000 nodes. Right, so we get those outputs. They're called logits. They're unnormalized, just outputs in these in this neural network layer. And then after that, we pass them through a softmax function, very similar as we discussed in the attention mechanism, softmax function, and this is our second softmax function for the transformer. Basically, what it does is it takes all those logits, those unnormalized values. We got 200,000 of them, one for each word in the English language, and it each one goes takes an exponent of each one and then divides by the sum of those exponents. So it basically creates a probability distribution. Now we have 200,000 values in a probability distribution, which in total add up to 1. And those values are representative of what is the probability for each word of the English language to be the next word in this sentence. But remember, this is a key. This is this is very important part of transformers. Something took me a while to figure out or wrap my head around. Like I had a big breakthrough myself, literally yesterday on this. That we had 6 vectors going into this 5th and final level, and then we applied the linear transformation. It was applied to each vector independently, and we applied the softmax. It was applied to each of those, vectors or whatever we got, those 200,000. For each vector, we got 200,000 of values after the linear transformation. And so the softmax was applied, we applied it 6 times. So we have 6 probability distribution. 1 for the word apples, 1 for the word are, or 1 as a result of the vector that we had for the word apples. We have a probability distribution of 200,000 values. Then we have another one as a result of the vector we had for the word are, another probability distribution of 200,000 values. And another one, and all the way up to delicious. We have for delicious, we also have, we had a vector, which was then converted into a probability distribution of 200,000 values, which add up to 1. So that's a very key, important thing. Now, in order to predict the next word in the sentence, we're going to take the probability distribution of the last word, of the word delicious, and we're going to use those probabilities, and we'll just take the word with the highest probability, and that will be our next word. So in this case, it will be fruit, right? So that we want the transformer to know that that's once the transformer is trained, the word fruit will have the highest probability in the probability distribution that came from the context-rich vector of the word delicious. The other 5 probability distributions, we're just going to throw them away. We don't need them. They're not used in inference. They're absolutely useless during inference.
So but they are useful for training.
They are.
Like, is that what we can?
Yes.
Okay. Because I was like, why are we doing all that compute for nothing? Someone should have thought of this.
I know, right? I know. Like, so imagine if you have an input of 100, like 1,000 words, like a context. That's why context window, is hard, because like if you have 1,000 words input, you're going to have 1,000 probability distribution. You're only going to need the last one of them, right?
For inference.
For inference, exactly. So we'll get to this in a second. So let's just sum up what we have so far, right? So the levels. On level 1 of our building, we have word embedding, right? We create turning words into vectors which contain semantic meaning. On level 2 of our building, we have positional encoding. We're adding positional encoding to these word embeddings because transformers ingest all of the input at once, not sequentially. That's their kind of like disadvantage, but we're making up for it with positional encoding to let the transformer know in which order these words actually came in the original sentence. And on level 3, we have the heart of the transformer. You can think of it as like it's in the middle. It's the heart is in the middle. It's the self-attention mechanism. Well, actually, the correct term for it is the masked multi-head dot product self-attention. So we haven't talked about the masked part. We haven't talked about the multi-head part. We'll talk about those separately. But it's called the dot product. You know why? We've discussed why it's a dot product. It's a dot product self-attention. It's attending to itself, to the sentence itself. So we've got the self-attention, and the reason why we need self-attention is we have vectors that have semantic meaning with positional encoding, but we actually want vectors that also have contextual meaning, because contextual meaning is extremely important in language. And that is achieved through the Q vector to do the query, and QK combination create the kind of like VLOOKUP, if you're thinking of Excel terms, or like the indexing, if you think of database terms. Like Q and K combination is the index, whether we want it or not. Well, K is the index, Q and K is like the answer, whether we want that or not, that in our context, and V is the value that we want to pull from each word into our context. So the QKV vectors together work to create the self-attention that's done through dot product, then a softmax, and then a weighted sum of V values. That's the self-attention part. And then after that, on level 4, we have the feedforward neural network, which has 2 fully connected layers. the first layer of the full feedforward neural network is in the original paper 4 times larger. So from 512, it goes to 2048 neurons. That's the first place and only place where there's an activation function. It adds flexibility, as John pointed out, to the learning. And then after that, it goes back from 2048 back to 512 dimensions. The next layer, that's our feedforward neural network. And then after that, on the final floor, on level 5, we have a linear transformation plus the softmax. Linear transformation is designed to go from 512 dimensions to the dimensionality of our vocabulary, for example, 200,000 words in the English language. And the softmax is designed to convert that into probability distribution. And all of this, very important to keep in mind always, all of this is done for every single word. So all the way, if we have 6 words, it's done for our 6 words. We do 1,000 words, we do it for all 1,000 words, all of these steps. Okay, that's the summary. All good?
Yeah. Wow. This is, as you know, as we talked about at the beginning of the episode, I've now been the host for over 300 of these episodes, and we've definitely never had an episode this deep in the weeds. It is a record. So
Awesome.
it's a bit of an interesting experiment. Like there's probably going to be some people out there that are like, wow, this is the most valuable thing that's ever happened to me in a podcast because it's so rich. But like as you said at the beginning of this section, when we got into the 5 boxes of Transformers, this might also have been, yeah, it tricky for people to track, especially if they don't have a neural network background. But very well done, Kirill. I mean,
Thank you.
certainly for this podcast medium, you are stretching the boundaries of what's possible. And I think for some folks out there, it's going to be a slam dunk.
Awesome. Thanks, man. Thanks. Yeah, and hopefully we'll do our best to include as many additional materials in the show notes. So if people want some references, we'll probably even I'll add some slides from the course. Like I'll just take some screenshots from the slides from the course. So we'll throw them in there as well, and so people can like follow along as well. In maybe there'll be some visual aids. We'll add them in there. If you are struggling to keep up, check out the show notes for the podcast. This is really important stuff for, like, I can't stress enough, so important for your future career. Like if you understand all these concepts, they're not extremely complex. Once you dig into them and get your head around them, it'll be a game changer for your future career. Like as we discussed at the start of the episode, I'm glad we did. Like LLMs are here for at least the next few years, are going to be disrupting businesses, industries. People are going to be building careers around them. They're going to be more and more pervasive. I don't know if that's the correct word, but proliferation. There'll be a proliferation of
Yeah.
LLMs.
Pervasive is right too, for sure.
Yeah.
They will pervade and more and more and more. Nice. Yeah. So this could be a good point. If this has already been an intense amount, this could potentially be a good spot in the episode to take a pause and kind of maybe simulate a bit of what has been covered. Because now we're going to expand on that so we're going to expand on the foundations, these 5 boxes, these 5 levels of transformers that Kirill's gone over, to talk about inference and training time. What we do at inference versus what we do at training time. And so, yeah, let's dig into that. So we alluded to this a little bit. So talking about, for example, having all those probability distributions for each of the words, but at inference time only needing the final ones. So maybe let's pick up from there.
Okay. Yeah. So just quickly, we're going to start with inference, and then we'll talk about training. With inference, indeed, you only need the last one. So let's say you have a prompt, and you with ChatGPT, you put in 1,000 words of a prompt into ChatGPT, and what it will do is it will ingest that whole 1,000. It will go through a transformer. As a result, it will have 1,000 of those probability distributions, one for every word, one as a result of the vector of each of those words. And we're only going to use the last one. So 999 of them are not going to be used. The last one, the 1,000th probability distribution, will tell us what the next word is supposed to be, right? So because this is because that context-rich vector, which we had for the 1,000th word, it had context about all of the words that came before it. So the probability distribution should be able to predict the next word. And that's exactly what we're going to do. We're going to pick the word with of the English language with the highest probability from that probability distribution. That'll be our first, or the 1,001st word. Now we're going to, what ChatGPT does next, how does it generate a lot of text? Like how does it generate like a whole paragraph of text? Well, what it does next is it takes this 1001 words now that we have, and it puts them through itself again. And as a result, we will get 1001 probability distributions. We're only going to use the last one, the 1001st. We're going to discard the first 1,000, and we're going to get the next word of the prediction, which is going to be 1002nd word. Now it's going to take the 1002 words that we have and ingest them again. And as a result, 1002 distributions, we only take the last one and get the third word or 1003rd word and so on. So it will keep generating words like that all the way until it generates an end of sequence token, EOS. That token, the EOS token, is also part of the vocabulary. It's one of those 200,000 words that we have. One of them is the end of sequence token. And when the probability for that token is the highest, it will be selected as the next word in the sequence or in the output sequence. And that will be a signal to ChatGPT or whatever GPT model to stop basically generating there. So that's how inference happens. And so when you see ChatGPT, when you ask a query and when you see ChatGPT entering one word at a time for you, like outputting one word at a time, it's not just like a cool thing they've done to make it look cool, like it's generating one word at a time. It's actually exactly how it works. Like transformers take in your input all at once, but they generate one word. Then they take all the input and generate. So every time it's re-invoking itself until it gets to end of sequence token. And also the other thing you might notice is like when you're speaking with ChatGPT in the same chat for a while, it gets slower. Like I've had this experience a lot of times. Like, and I'm, I don't work for OpenAI, so I can't comment on this exactly. But my guess is that what is happening is that it's taking all of your previous conversation and putting it into itself, right? So it's generated a paragraph of output. Now you ask another question. It's taking your question plus everything you had before up to the context window limit, which right now I believe is like 32,000 for ChatGPT. It's taking all of that, putting it back into itself, generating more, and so on. So the more you talk with it in one chat, the more slower it will get until it reaches that context window, and then it's just going to be the same amount of slow going forward, as I understand. So that's how inference works. That's how it generates new words. I guess the only other comment here is that what we discussed here so far is called greedy sampling, where you have this probability distribution, you take the word with the highest probability. There are other sampling techniques. For example, you could take the three words with the highest probabilities, and then take a random one of those three words. And when you click in ChatGPT, you click regenerate output, that refresh button, it will give you a different answer more often because it's not using greedy sampling. It's not always just taking the words with the highest probability. It's mixing it up a little bit to give some variability of the output. So that's inference.
Nice.
All good?
And to really quickly there, the at the time of recording, the OpenAI model with the largest context window is GPT-4 Turbo, also known as GPT 4.5, and that has 128,000 token context window. So that's about 300 pages of text that it can handle in a single prompt.
Yeah, that's quite a massive context window. Okay, so now we're going to talk about training. Training is where transformers are super, like where they are super efficient. They're the state of the art. Like as we discussed, they're not so efficient in what's it called? They're not so efficient in inference. They could be more efficient. They are redundant operations, but in training, they're like the best. So what we do is we take a large corpus of text. Just think of, for example, all of Wikipedia, lots and lots of data, lots and lots of text in there. We take this text and we break it down into segments. Typically, segments are just basically chunks of text that are the size of the context window. So you just take all of Wikipedia, put it into one huge document, and then you break it up into context window segments that fit exactly into the context window of the transformer. Then each segment is fed into the transformer one at a time for training. This, of course, can be parallelized. Now, we're going to look at what happens with one segment when it's been trained. For simplicity's sake, we're going to take a smaller example. We're going to take the sentence we've been working with. We're going to take apples are a type of delicious fruit, which has total 7 words, and we're going to pretend that's our segment and see how the transformer is trained. Right. So you would think that what would happen in this kind of scenario is that you would take apples are a type of delicious blank, right? You would take out the last word, you would feed in the everything except for the last word, and you would want the transformer to predict the seventh word. That's what we are naturally kind of inclined to think. Well, at least me, with my limited exposure to, or the amounts of things I've seen about AI, like I'm like, okay, that's probably the way it works. But actually, it's much smarter than that. Architecturally, transformers blow everything out of the water. What happens is all 7 words are fed into the transformer, and then all 7 of them go through these 5 levels we talked about, or 5 levels of our building. So the token embedding, positional encoding, the self-attention mechanism, that feedforward neural network, and the final linear transformation plus softmax. But let's go back to, and then we get these probabilities. For each one of these 7 words, we have a probability distribution, which results from the vector that word was represented by. But let's go back to the softmax. And this is where we go back to the pin that we put in our conversation earlier, John. Basically, the masking. So what will happen is the transformer has this additional mechanism inside the attention mechanism, which is called masking. And it doesn't allow any word to look at the words that come after it. So, for example, in the case of apples are a type of delicious fruit, the word apples will only, when it's doing the QKV mechanism, it'll only be allowed to look at itself. It can't look at any words going after it. The word are, so apples are, so the word are can look at itself and apples, but it cannot reference any of the words that go after it. The word type, which is the 4th word in our sentence, it can only look at apples are a type. So you can only get context. It's allowed to only get context from those words. It's not allowed to get context from the words come later. And the apples. Yeah.
Yeah, a really key thing here, though, just to reiterate for our listeners, is that this is for these decoder only models like the GPT series models. If you have some other architectures, like the BERT model that we talked about now quite a long ways ago in the episode, that kind of encoder architecture, the B in BERT stands for bidirectional. And so it can actually use information from the future of the sequence, because with that kind of encoding model, we're not interested in predicting the next word, which fundamentally you can't. If you knew what the next word was going to be when you're trying to do next word prediction, that's cheating. You don't need a model to do that. You just know what it is.
Yeah.
But when you're doing an encoder type of transformer, that extra context of what's happening ahead of a given word can be useful and can be used for some downstream task.
Yeah, for sure. And that's also like you're right. This masking is only applied in the decoder part. In the original paper where you have encoder and decoder, the encoder, like it's used for translation. So the encoder can look at everything. When you're translating a sentence, you're able to see the whole sentence, and then you generate word by word your translation. So in that case as well, there's no masking in the encoder. So you're absolutely good point. That's only a decoder thing. So you have this masking. So depending on the word position, all the other words to the right are, or the later words are masked. And it's also called triangular masking. The reason why it's called triangular masking is if you write out all these words in a matrix, like as the columns and the rows. So you take apples are a type of delicious fruit. You write them as the rows, and you write them out again as the columns. You'll have a matrix of 7 by 7. And on the left, the columns are going to be which word you are creating a context-rich vector for, and the columns are represent which words that context-rich vector can reference, is allowed to reference. Well, the way it works is like the first row will only have the first column, right? Only apples, it can only reference itself. The second row can reference 2 words, apples are. The third row can reference 3 words, apples are a, and so on, and so long, so and so on. So basically, you will notice that in the top right corner, you have this triangle forming, which is like those words are blacked out, like they grayed out. They're not allowed to be referenced by that the word that we're creating a context-rich vector for, which is in that associated row. And so that's why it's called a triangular mask. And that's how we create these context-rich vectors. And the mathematical way that it works is it's very simple. It's basically once you calculate those dot products, and before you apply the softmax for the words that you're not allowed to reference, you add this triangular mask, and it basically where the words you are allowed to reference, the mask has a 0. Where you're not allowed to reference, it's a negative infinity. So effectively, you're replacing the dot product. You calculate the dot product for each one of the words, but where you're not allowed to reference that word, that dot product is replaced with negative infinity. And when you apply the softmax, it'll become a 0, right? So when you do the weighted sum, it'll be a 0. So it won't allow you to get to the v value behind the word that you're not allowed to reference. So that's how the masking technique works. And effectively, what we get in the end, so in our case, we have seven words. Apples are a type of delicious fruit. In the end, we will get, after the 5th level, we will get a probability distribution from each one of these vectors. And if you think about it, because let's take the word, for example, apples, it was only able to reference itself. It didn't know in the attention mechanism, it didn't know what else is happening in the transformer on the next words. And moreover, as we discussed, the vectors in the transformer never get mixed between each other. The attention mechanism is the only time when the vectors can somewhat reference each other. So the word apples, along the whole time, the vector for the word apples has only been exposed to the vector for itself, the v vector, the kqv vectors for itself. So effectively, this probability distribution that we have from the word apples is a probability distribution as if our segment only had the word apples, and it predicts what the next word should be, right? And if we take the apples are, and we look at the probability distribution that we got from the context-rich vector for the word are, right? That context-rich vector was only allowed to reference the words apples and are itself. It wasn't allowed to reference anything else. So the probability distribution that we got from the word are is as if we were doing a segment with just 2 words, apples are. So it's predicting the next word. And then we keep doing that. So for example, apples are a type. For the probability distribution of the word type, well, the vector that it was based on only ever referenced apples are a type. It never saw what's coming next in the sentence. So it's as if that probability distribution would be the same if our whole segment was only apples are a type. So it's predicting the next word, right? So now all of a sudden, these 7 probability distributions that we have, we in one go, instead of one training, we can do 7 trainings, right? We can calculate 7 errors because the probability distribution for the word that we got from the word apples, from the context-rich vector of the word apples, should be predicting. We wanted to predict the word are. The probability distribution we got from the context-rich vector of the word are should be, we wanted to predict the word a, and so on and so on and so on. The one we got from the word type, the 4th word, should be predicting the 5th word. The one we got from delicious should be predicting fruit. The one we got from fruit is still useful to us because it should be predicting end of sequence, right? The next token after is end of sequence. And because that probability distribution has context of the whole sentence. So all of a sudden, we can calculate not 1 error, we can calculate 7 errors, and we can calculate the loss function of 7 errors, backpropagate it through the whole neural network, and adjust our weights. So this was a simple example. Now imagine you have, like we discussed at the beginning, you take the whole of Wikipedia and you break it out into segments which are exactly the size of the context window of, for normal ChatGPT 4, 32,000. Now, in one go, the transformer calculated 32,000 probability distributions, and in one go of the transformer, you get to train it 32,000 times. You get 32,000 errors, you calculate the loss function, you backpropagate it. So effectively, this is the mind-blowing power of transformers. You're getting within segment parallelization. You can parallelize it across batches. You can send, you can do a batch of segments at the same time across different machines and then calculate the loss across batches and backpropagate it that way. But also within each segment, you're getting parallelization. So transformers, and this is like extremely powerful insight. Transformers are super powerful, not only because like they're efficient in matrix operations and they're elegant in their solutions and so on, but one of the biggest advantages is that they have this double parallelization, the within segment parallelization that we just described, and also the parallelization you can achieve through hardware, which is batch parallelization. And through this double parallelization, that's why you can throw a lot of money at it, a lot of data, and you can train. The more basically GPUs you can put towards it, the more money you can throw towards training it, the more you can get out of it, because it just parallelizes so well. And this is a very inherent architectural by design solution of transformers that we're taking advantage of these days.
Nice. So now going back to my question from a while ago, when you were getting to the end of your 5 boxes of transformers, your 5 levels of transformers
Yeah,
conversation, I was I was talking about, oh, like, why would we create all of these vectors for every one of the words? Certainly for
yeah,
inference, it doesn't seem like we need it, and you agreed. Now the whole picture makes sense. So that during training, we're not just trying to predict some of the words. We use all of the training data that we have. We might as
yeah,
well, like you were giving, like the apples are. Apples are
yeah,
a type. Apples are a type of delicious. Like you might as well, you have all these training data, and so you can use each one of these steps in the sequence of tokens. So if you have, yeah, like if you have all of Wikipedia to train on, then you might as well train at each next word in Wikipedia. And if you have all the internet to train on, then train on each next word on all of the internet. That's
yeah.
going to give you the most amount of training data possible. Very cool. And then, so just one kind of question for you is, I guess, the correct token. So in that 7 word sentence that we've been working with throughout this episode, apples are a type of delicious fruit. I guess the correct token to be predicted after that is the end of sequence, that special EOS token. Yeah.
Yep, exactly. Yeah, that's the correct token. That's what because that's uh, segment our segment. It's more like there is a bit of like additional tweaks that you need to do. Like if you're taking all of Wikipedia and you're breaking it down by context window, well, your context window might just end up being in the middle of a sentence, so the end of sequence token might not be the correct one to be predicting afterwards. So you might, like it's architectural choices. You might break it down differently. You might stop it a bit earlier before the 32,000 or the context window size at a full stop or at the end of the paragraph, or you might choose not to use the prediction of the last token because you're not sure that that's the end of sequence token. So that's kind of like more detail, nuanced things. But in a nutshell, yes, in our example, it would be the end of sequence. And the other thing you pointed out there, which is very valid as well, very important, is that by doing it this way, we're exposing the transformer to variable lengths of input, right? So we don't have to feed it, 5 word sentences, 100 word sentences, 1,000 word sentences separately. We just give it the context, the maximum we can, and inherently by design is going to train on 1 word sentences, on 2 word sentences, or 3 word sentences, on 4 word, all the way up to your context window size. So it's an additional like um, automatic advantage of transformers that you don't have to think through how you're going to train them on different sizes of data. You can, like again, you can make that more nuanced if you want to, but ultimately it's inherently built in that it's already training on all variability or all variations of input sizes.
Nice. All right. So you've given us an amazing introduction to transformers, to attention, and therefore to large language models. Why ultimately are transformers so powerful? Why, when we take this attention mechanism that you've described, these 5 levels of the transformer, and we scale it up using all of the parallelizations that you recently described in this episode, why is it the case that all of this ends up being able to be, at this time of recording, by far the most nuanced, mind blowing tool that humans have ever created?
Yeah, indeed. Like it is really mind blowing. It's very cool to watch talks of the creators of Transformers. Like I found one of them on YouTube, and like it's really cool how to these 8 people. It's really cool to see how they were thinking when designing this, and like each one of them had separate roles, and they're identified in the research paper. And by the way, like the order of names on the research paper is not alphabetical or in order of contribution. It's at random because they all feel they equally contributed, and it's very interesting to observe their thinking about how they were building this architecture while having in mind speed, like speed and parallelization. They like all of the solutions they were coming up with. They were considering that, and I think that that's probably one of the biggest reasons why transformers are so powerful, because they use matrix operations, which are really fast. There's no, like in LSTMs, there's no gated units and all those kind of other solutions to the vanishing gradient problem that had to be put into LSTMs. There's no bottleneck that LSTMs had. Transformers are non-sequential as opposed to LSTMs, so they don't take the input one by one. They can take the input all at once. So that's why if you type in, like, if you put into a chat GPT, like, I don't know, 2,000 words of input, you get an answer right away, right? Like, it starts typing your prompt is 2,000 words, but you start seeing the result right away because it's not processing them one by one. It gets ingested all at once. And of course, this double parallelization. I don't know if this is a completely correct technical term. Like, it's something I used to describe it for myself. The parallelization within segment that happens through this wonderful, just genius solution of triangular masking during the attention mechanism and the inherent architecture of a transformer, plus parallelization, which you can achieve through batches with, which is hardware based. I think when you combine all of those things, it just like any model that is able to process all of the language that we have online on the internet, it's like a perfect storm. We have so much language that we've been creating since the 90s that's available on the internet. Any model that can process all of it is going to be powerful. It just so happens that transformers were built with speed and parallelization in mind, and that made them the king in this moment.
Nice summary. Very nicely
Cool.
done.
Can we do a quick bonus trivia? I got a few extra points.
Go for it, Kirill.
All right. So GPT model, what we discussed, those layers, right? Let's start with the attention head. So inside the attention block, remember how we said we create three vectors, the QKV vectors. They're 512 dimension each. So from the vector that has semantic meaning plus positional encoding, we create the Q and K and the V vector for each word. Well, actually, you can. That's one attention head. In reality, the transformer, the original paper has 8 attention heads. And how is that done? Well, the original vector that you have with the semantic meaning and positional encoding goes through a matrix, or is transformed with a Q matrix, but that matrix creates not a 512 dimensional vector, it creates a 64 dimensional vector. And there's a K matrix, which creates a 64 dimensional K vector. And there's a V vector matrix, which creates a 64 dimensional vector. But then there's 8 sets of those matrices. There's 3 matrices, QKV 1, and then there's QKV 2, there's QKV 3. There's 8 sets of those matrices, and so you get 8 attention heads, which are running in parallel, so the transformer can learn different things about the same sentence. It's an important thing to keep in mind is that if I was doing an interview for somebody applying for an LLM job, I'd ask this question. When you're doing multiple attention heads, is your input vector for this attention mechanism, which is the vector with the semantic meaning plus positional coding, is it split up into 8? Is it like cut into 8 parts? The answer is no. It's not cut into 8 parts. It goes through a matrix or linear transformation, a matrix operation, which spits out, like the 64 dimensional vector of the Q1 matrix, the result of the Q1 matrix, the 64 dimensional vector. It's actually a combination of all 512 dimensions. So you're not separating the dimensions of the input vector, you're combining them to a smaller output. So that's number one, multiple attention heads. The original paper has 8, you can have as many as you want. I believe the GPT-3 model had 96 of them. In addition to all of that, like imagine everything we did, we had like a building of 5 floors, right? And on the level 3, we've just discussed there's going to be 8 attention heads or 96 attention heads. Great. But now take that building with 5 floors and put another one on top, and another one on top, and another one on top, 96 times. So the GPT model, it's again your choice how many you want to do. The transformer architecture has 6 layers. So these are layers. So after the output of these 5 levels, instead of predicting the next word, those outputted vectors that we got, the context-rich vectors after the feedforward neural network, they go as inputs into the next level, into the level 1 of the next building. And then we get outputs again, and then go in. So that happens 96 times in the GPT-3 model. And why is that? Well, that gives it even more opportunity to learn, gives it more to learn more complex relationships in the language, understand more complex concepts. Like how can ChatGPT answer questions on chemistry, right? Like that's a level of sophistication, or poetry. That's a level of sophistication that might not be achievable with one layer of one encoder, a decoder. But when you put 96 decoders on top of each other, well, it looks like it's able to do really phenomenal things.
Well, so making sure I'm getting this right. So 96, you said that number twice for GPT-3. So there's both 96 attention heads
In each
as
decoder.
well as in each decoder, as well as 96 layers of decoders.
Yes. So there's 96 squared attention heads if you calculate all of them correctly.
Wow.
Right. That's not the original design. And um, with new models, things might be changing. And
Yeah.
I would urge people to double check this number. But the original design was 6 layers of encoder decoder architecture with 8 attention heads inside each layer. In GPT, in ChatGPT specifically, they took it to the next level with 96 layers. And as far as I remember, 96 attention heads inside each layer. And I guess the other part of bonus trivia is we already talked about that the original paper was written for translation tasks. GPT is just a decoder part, which is for generation. Um, and of course, like GPT can also do translation, interestingly enough, but we're not going to go into detail on that. The other thing I wanted to point out is, for me, diving deep into this really helped to understand that ChatGPT doesn't have any reasoning or logic behind it, right? It doesn't understand and cannot think. It cannot answer your questions through thought. It can only answer your questions by predicting the next token. But it still stands up to debate. It's good to understand that. It's good to, like, it helps me better perceive these large language models and like what they're doing. Like that they're not gonna, like, on one hand, they're not gonna take over the world because they can't think for themselves. They can't have a reasoning. On the other hand, like Ilya Sutskever, who's in OpenAI and who's part of these research papers that we talked about at the start. There's a YouTube video of him talking to an interviewer about this, and the question is, like, maybe this is a new kind of intelligence where you don't need reasoning, but predicting the next word is sufficient in order to behave like a human, in order to think like a human, in order to create things like a human. And so it still stands up for debate. But at least knowing um, the difference in like how we think and how we reason versus how a GPT or a large language model reasons, for me, it's been really helpful.
Very cool. Very cool, man. What an episode. It has been epic, truly.
Thanks, man.
And I've learned a ton. Kirill, I can't believe how much you and probably Atma now know about attention, about transformers, about large language models. Wow. And so, yeah, your course must be incredible. I am now itching to take it. So, yeah, large language models, A to Z, available in the superdatascience.com platform exclusively.
Exclusively.
Fantastic.
Check
Kirill,
out,
before I let you, oh, yeah.
sorry, John, just quickly check out superdatascience.com/LLM course. You will see there the curriculum, the description, some images. So it just gives you a quick overview before you decide if it's the right thing for you.
Nice. And of course, we'll be sure to have that link in the show notes. Kirill, before I let you go, as you know, having created that document for me to interview people from, before I let guests go, we must have a book recommendation. Do you have a new one for us since you were last on the show last year?
I'm not sure if it's a new one. I may have mentioned it on the show before, but I think it's fair for me to mention it because I am rereading this book myself for the second time.
Ooh.
The first time Adlan and I, it's not a technical book. Adlan and I first time listened to it in a road trip, actually through Slovenia. We were on a road trip with Ivana and her husband Mitya. Ivana is one of
Yeah,
the people who contributes to this podcast.
yeah, Ivana is the podcast manager. She is the most important person on this show. She is the one, 2 episodes a week. They don't happen every single week at exactly the right time for many years without an unbelievably diligent person. And yes, Ivana in
Absolutely.
Slovenia is that person.
So yeah, we were on a road trip there with Hadelin. That's when we listened to it the first time, and recently I felt the need, I felt the time came to re-listen to this book. The book is called The Big Leap by Gay Hendricks. It's over 20 years old. It's a fantastic book that, like, the main two kind of takeaways is, um, where are you operating in your life, whether it's your personal life, your romantic relationships, your work life. Are you operating in a zone of incompetence, a zone of competence, a zone of ex- expertise, or a zone of genius? And he talks about how to identify that zone of genius for yourself in all these areas of your life, and why it's so important, and also what prevents us. And the second takeaway, big takeaway that I remember from back in 2017 is the thermostat principle, that whenever things are going well in life, like, your body or your mind operates like a thermostat. Like, if things are going, if you're used to a certain level of happiness or finance or whatever else, romance in your life, and things go worse, you will find ways to get back to where you were. But interestingly, conversely, if things get better, you'll also push yourself back to where you were. And that's why, for example, we see the stats around lottery winners. More than 80% of them lose all their money within 2 years, because their psychology takes them back to where they used to be. And I think entering this new, if I can tie it into the times we live in, entering into this new age of where there's going to be a lot of change happening, with 2024 bringing in even more probably AI developments. I think it's extremely important to um, be conscious of your psychology and to enhance your psychology, because, as they say, success, however you define it, however you measure it, is only 20% mechanics. It's 80% psychology. So it's really important. Like, I feel in my life, I'm ready to take the next step in many levels, in many layers, and I feel like that's why I felt the need to reread this book again, to help me prepare my psychology for that step.
Your life has many levels, many layers, and many attention heads.
96.
Squared. Uh, awesome, Kirill. So, yeah, thanks so much. If our listeners aren't already aware from your many previous appearances on the show and your countless courses and everything else you've done online for millions of people, how should people be following you if they are new to you?
Great. LinkedIn, great place to follow if you like. And also Super Data Science membership, where we've just revamped it, and we've got a community, we've introduced community aspect. And so I'm hanging out there probably like twice a week at the moment. I'm going to be hanging out there almost on a daily basis. You can hit me up, chat. We will be having these interactive sessions, get-togethers, parties, whatever else, workshops. Definitely, if you want to interact in person, that's the place you can find me.
Nice. In person, you mean
I
live?
mean, live. Sorry, yeah, live. It's becoming so so
Virtual.
normal, right? Virtual in person.
Virtually in person. Uh, nice. All right. Thanks so much, Kirill. It's been so awesome catching up with you and having all these insights, these deep, deep insights that you and Adlena have dug up about LLMs, about transformers, about attention. Thank you so much. And I'm sure we'll be catching you again sometime soon.
Absolutely. Thanks a lot, John. I really loved it.
Well, I hope you enjoyed that extra technical episode. In it, Kirill filled us in on the development of attention in natural language processing, the 5 stages of transformer data processing, specifically input embedding, positional encoding, the attention mechanism, a feedforward neural network, and linear transformation and softmax. He talked about how encoder-only transformer architectures like BERT are efficient for natural language understanding tasks, and how decoder-only architectures like the GPT family are best suited to generative tasks. He also filled us in on how transformers are used for both training and for inference, and how they're scaled up to enable the powerful emergent capabilities of LLMs. As always, you can get all the show notes, including the transcript for this episode, the video recording, any materials mentioned on the show, the URLs for Kirill's social media profiles, as well as my own, at superdataScience.com/747. Given how unusual and highly technical today's episode was, I'd particularly appreciate if you reached out to me to let me know. So perhaps by commenting on the social media posts that I make about today's episode, to let me know what you thought about having so much technical content in an episode. We're definitely trying something different. And so let us know whether we should do it again or maybe not. All right, so thanks, of course, to Ivana, Mario, Natalie, Serge, Sylvia, Zara, and Kirill on the Super Data Science team for producing another exceptionally deep episode for us today. For enabling that super team to create this free podcast for you, we are deeply grateful to our sponsors. Please consider supporting the show by checking out our sponsors' links, which are in the show notes. And if you yourself are interested in sponsoring an episode, you can get the details on how at johnkrohn.com/podcast. Otherwise, please share this podcast, review it on your favorite podcasting platforms, subscribe if you aren't a subscriber already, but most importantly, just keep on tuning in. I'm so grateful to have you listening, and I hope I can make episodes you love for years and years to come. Until next time, keep on rocking it out there, and I'm looking forward to enjoying another round of the Super Data Science Podcast with you very soon.